Today we're going to talk about titrations. It's a very useful technique if you're in the lab. It's extremely useful as you'll see today. Today we're going to talk about the fundamentals, basically how titration works, and then calculate titration curves and also interpret some useful information like pKa and the concentration. And yeah, some of you are already using titration, I guess. And as you see, this is a very useful technique. So let's talk about what is titration first, and then why we need this technique could be a complementary to what we had before. So before we had species, and we knew what kind of species we have in the system. Let's say we had A, B, we had H plus, so we had also pH. Then we know how to construct equations. And then we know how to solve it. So we had three approaches for solving: graphics, the spreadsheet, also algebra. Eventually, we were getting the concentration. So that was the pipeline of what we were doing before, and so on. All of the concentrations at equilibrium. But this pipeline was doable because of the very first step. We knew what we have in the system. So that's the first thing. Also, we knew about some of the features, for example, the equilibrium between the species, some information that we use to drive these equations. But this is not the case all of the time. Sometimes we have some samples with some unknowns. So titration helps us to get there, to get to this part, hopefully, without knowing what species we have in the system. So we need to know how we can use titration to get there. So in titration, the pipeline is basically in terms of the species. It's not clear. So we don't know really what is the equation. Therefore, using the approach we had so far, basically this is also not clear, or it cannot be calculated. Yeah, it's okay, now I try my best not to touch it. So titration, I think we highlighted the importance. This is to figure out the properties of water, such as the concentration and pKa, without knowing the species. We use the titration technique. So generally speaking, the titration is basically mixing something that is known to something that is unknown. So that's basically the general concept. But for, yeah, this is very... But for acid-base titration, we add again the same thing, a known amount of acid or base to a solution that we're interested to study. And the resulting change in pH is what we're looking for, or what we're studying. So, and then we look at basically the change. So it's a mixing of something that we know and something that we don't know. So this could have potentially two important interpretations. The first one is the unknown acid or base present in the original solution. We can basically talk about that and figuring out what we have there. So that's what we're looking for in this lecture. So basically the whole idea of titration. Or the second is basically looking at other similar phenomena that we have in the nature. For example, here it's showing two different examples, how we're mixing something that it has known composition. In this case, for example, the calcium oxide to the river, and then figuring out what happens after. Well, in this case, it's just basically a mix of two rivers. Yeah, this is... So it's basically a known amount of what we have or what we know, to a sample that we're interested to study. That's basically the whole idea. And specifically, we're targeting sort of an acid-base kind of behavior. And to review quickly what we talked about before, we know when it comes to acid-base, some systems, in this case, it's a weak acid, is not sensitive. This region is not sensitive to pH. But as you get closer to pKa, we see that we have a sharp decrease in the concentration. So some parts are very pH sensitive, some parts are not pH sensitive. So we will see that kind of behavior when it comes to the actual titration experiment. So we're basically using this feature of a weak or strong acid system. So qualitative description of titration. As I mentioned, we have basically two things. One is the known. Let's say we have a vial or a pipette with a concentration of, let's call this known. For example, this is 2 molar HCl, something that we know what is that and what's the concentration. So we call this titrant. We're adding this to something that is unknown. So we have a control on how much we add it. For example, by knowing the concentration of and volume, we can calculate how much moles we introduce from the titrant to the system, to the unknown. And then we're basically measuring the pH. So basically, we have a pH probe that is measuring as a function of how much we added of the titrant to the unknown as a function of time, which is basically, because we're dealing with equilibrium, it's basically as a function of how much that was added. So more specifically, if we call this one the pH probe part 1, this one 2, and the unknown 3, then what we're interested to do is basically we're looking at the pH, we're reading the pH, which is what we're getting from the probe, as a function of how much of added known. So we know how much we added, basically. And we trace the pH. So we get the profile of this guy, and this would be the pH of unknown. So it's very straightforward. From the execution point of view, it's very simple. You just need a pH probe, basically. You bring an acid or base that you know, for example, 2 molar HCl, and you add it to any sample, any aquatic sample, regardless of whether you know the composition or if you don't know the composition. And then you basically trace the pH. So the whole point of this lecture is basically how to interpret this data that we're getting. So operational wise, this is very straightforward. But now we want to see what kind of useful information we can get from that simple curve that we're getting. So first, talking more quantitatively about what's happening. If we add, let's say, the sample, the unknown is just pure water. If we add acid, the pH goes down. If we add base, the pH goes up. And this would be a typical classic behavior. If this is basically how much acid we're adding, and this is a pH of water, we have a significant decrease of pH from 7 to 2 when you add a tiny amount. So it's so sensitive to adding water, to adding acid. So in this case, I'm adding HCl. So it's producing H plus directly. From the first lecture of this chapter, we know this is fair to assume fully dissociated acid for strong acid. So 1 mole of HCl results in 1 mole of H plus. And this will directly impact the pH very strongly at the beginning, and then it gets to a plateau. And if we do opposite, add base, then again, this is a pH of water. This is what exactly we were looking for. This is the water pH, and this is how much of the known we added. So in this case, it's basically the base. And as we were expecting, adding a base increased the pH. So two things happen. First, we know how much we added, the x-axis. And then we looked at the profile. We were expecting a decrease in pH, but this sharpness, this sharp decrease is something that we can later use to gain information about the system itself, which in this case was pure water, pretty straightforward. So now let's assume we're adding acid as a known to a base as an unknown. So what we have here, assume we have a bath of sodium hydroxide. We know if we have sodium hydroxide, it fully dissociates to sodium and hydroxide. And then we bring this acid and we add it to the solution. And this is basically an HCl. So we have H plus, Cl minus, and then here we have sodium and hydroxide. So now we change pure water to a sample that contains some sodium hydroxide. And we're still adding the same acid. This is very... Okay. A little bit of engineering might help. Okay, we'll see. So right now we're adding H plus directly from HCl. But what happens when we add HCl or when we add H plus? In the case of pure water, it was directly impacting the pH, like very sharp, very quick. Even the tiny amount was enough to bring the pH down from 7 to 2. So what happens now? What changed now in terms of the sample? We have sodium now that we didn't have before, and we have hydroxide. Any of them might interact with the proton that we're adding? Yeah, exactly. So in this case, H plus that is introduced from HCl would be combined with OH minus to form water. And this is basically from sodium hydroxide. So what it means is that we're introducing acid, H plus, but H plus is not impacting the pH. Rather, it's been consumed by hydroxide that is there. So what it does is it delays in pH zero. Delay, it doesn't mean in terms of time, but rather in terms of how much we're adding proton. So let's say if this was an acid added, And this is a pH of the sample. If this was for pure water, how does it look like for sodium hydroxide? How does the delay would show up in this figure? So we add H+, it doesn't impact the pH. We add more and more. At some point, we're running out of hydroxide that is originally coming from sodium hydroxide because we had limited amount of sodium hydroxide in the system. So it will be fully consumed. And then that 1 mole of proton that we're introducing after that point then results in pH drop. So how does it look like then, the figure? Any thoughts? Is it something like this one? No, what is it? Exactly, so something like this one. So initially, you're adding acid, but it doesn't impact pH, but you are adding acid. So in terms of the x-axis, you're progressing. However, the pH drop, you don't have it. It's that delay. And then at some point when you're running out of sodium hydroxide, it will be 1 mole of sodium, 1 mole of proton will translate into the change in pH or impacting that water hydrolysis. Make sense? So this would be...
HCl acid now?
So, yes. So you have a glass of water, just pure water, 1 mole of acid, you add it. There's nothing, nowhere to go. It will be translated into increasing the pH or impacting water hydrolysis reaction, to be more precise. 1 mole directly impacting the pH. And now you have sodium hydroxide, tons of hydroxides hanging around. Then 1 mole of pH, it will be consumed by 1 mole of hydroxide. So it doesn't impact the pH. So you added 1 mole, but then it doesn't impact the pH. And then 2 moles, still it doesn't impact. But at some point, you're running out of hydroxide. You turn all hydroxide to water. And then 1 mole after that point, it will result in a sharp decrease in pH. So it seems this delay is related to the concentration of what we had in the sample. Yeah. So keep these 2 words in mind, known and unknown, or titrant and the sample. We're interested to know more about the sample. We already know about the acid, and the pH that we're measuring is basically the pH of this guy. So this is an external factor we're adding to this boundary of the system. So this is a classic titration curve. Very quick interpretation from this graph is that this is, it seems related to the concentration of what we had in the sample, what we're interested to know. That's about the qualitative information or qualitative description of titration. Now let's focus a little bit more on the quantitative interpretation, because it seems this is a very useful technique. And to do that, we design 4 different scenarios. Always, the titrant, the known, is either strong acid or strong base. We're not considering adding a weak acid or base, because weak acid or base, it's already weak. It won't change the pH much. So we might need to add 1 liter, for example, of that acid to be able to see the pH. So it's not effective. Conceptually, we can do it, but it might not be effective all the time. Rather, the sample or the titrant is always acid, strong acid or strong base. So let's put that aside. But for the sample, we have 4 different scenarios. The first scenario is that what we had a strong acid or base in the sample, the previous page, right? That was just sodium hydroxide. In the next one, obviously, if we have a very weak acid, inside that sample, and then it goes by like different scenarios. So now the first scenario, we have strong base or acid in the sample, and we're titrating this solution containing, let's say, sodium hydroxide, 10 to the minus 3, and we're adding strong acid. It really doesn't matter what kind of strong acid, and it really doesn't matter what kind of concentration. It's eventually about the mole that you're adding. So if you have the concentration, you have control on the volume of that pipette, for example, that you're adding, then you can just basically do that, as long as this is a strong titrant. So let's say the sample itself is sodium hydroxide, and we're adding HCl. What species we have then? Because this is one of those cases where we already know the speciation. H plus and OH minus, as always. Na plus that existed in the sample, and Cl minus that we're introducing to the system. And what is the initial pH of this sample before we add acid? And we can calculate it, but very quick. 14 minus 3, so it's 11. So 10 to the minus 3 sodium hydroxide is roughly 11. But we can basically calculate that. So the initial pH without adding acid is 11. Obviously, if we do add acid, eventually the pH goes down. A little bit of resistance at the beginning, it won't change the pH, but then as it goes by, then we have that sharp decrease, or we depleted all the base that existed. So now let's approach this just from what we had in the first lecture of this chapter. We had charge balance. What is the charge balance here? Exactly. All the cations equal to plus Cl minus. So in this, just before we talk about the other equations, which one of these four is fixed? Or tell me about which one changes? H plus changes, right? Yeah. That's the pH that we're interested. Obviously, if H plus changes, OH minus also changes. What about sodium? It's always fixed. And we're assuming sodium hydroxide is not going to happen. Sodium hydroxide is fully dissociated, doesn't come back. And there's no further reaction for sodium. In some cases, in the future, it might be, but in this case, very simple, it won't. So this is a fixed value. How about Cl minus? We're continuously adding, so it's variable. So this is variable. So this is not like a classic charge balance we had. Slightly different because the approach is different. This is more like a dynamic system. So we can have a few more equations. So from the equilibrium, we know OH minus is equal to Kw over H plus. And from the mass balance, as we talked, we can do mass balance on the sodium concentration. Let's call this total sodium. And the value is already given, 10 to the minus 3 molar. This is one of those cases that we know what is in the system, and we know what's the concentration of that species. What about in terms of the mass balance? How about the Cl minus? This is always equal, changing, right? And it's almost always equal to the total amount of acid that we're adding. Or let's call this C of acid. And we know how much we're adding, right? if you added 1 milliliter of that titrant to the system, you precisely know how much you added in terms of the volume. It's just basically a simple pipette. Or if you have more like a fancy titrator, they can actually measure the volume that was added. So that CA is something that we know already, and it's changing. It's a function of how much we added to the system. So now let's put all of them into charge balance. When we do that, it's H plus total sodium is equal to Kw over OH minus plus that Ca. And if we rearrange it, we get to this equation. So we're mathematically driving an equation that can describe the titration profile. Here we have, this is a constant, this is a constant, but this is a factor that we're controlling. So basically what we do is we add some concentration of acid. So we add Ca. Then we have a quadratic equation, right? Then everything is clear. The only thing is we calculate pH for the solution. So we solve H plus concentration, therefore the pH. So then we have 1 point in this graph. So our Ca would be our x-axis, and then the pH would be our y-axis. And if you do that, this would be basically the curve. So the algebraic solution, what we had, lecture 8, we didn't have this term. And if you calculate the pH for Ca0, Ca equal to 0, then you get that pH of 11, initial pH of 11, which is basically the case here. So this is, no Ca is added. So this would be initial pH. And now you're changing that Ca term, just the constant is changed for that quadratic equation. Then you solve for that. And then you get 1 more point in terms of H added. So this is Ca. And then the pH on the y-axis that you're basically calculating. And in terms of the unit, this is milli equivalent per liter. So milli equivalent, just that equivalent per liter, consider that to be molar, equivalent of the acidity you added. But then for here, for the sake of simplicity, equivalent per liter is like mole per liter, so it's molar. So milli equivalent is millimolar. So this is basically millimolar. So now mathematically, we also observe that delay that we just talked about, qualitatively talked about. Now we have this part of delay. So here, you're adding acid, you added 0.5 millimolar of acid, but the pH barely changed from 11 to maybe 10.8. So it's resisting so much. That resistance is basically the topic of the next lecture would be buffers. So basically you're dealing with some buffer zone, resistance, again, changing the pH when you add H plus. And after the delay, it's depleted, and then you have this sharp drop in pH. So this is basically sharp drop in pH. So quantitatively speaking, how much resistance we have here? It's 1 millimolar, right? Is it related to the concentration of sodium hydroxide? How much was the concentration? So also 1 millimolar. So it seems it's directly related. So in the future, if we don't have the concentration, we can basically do a simple titration and calculate the concentration. I think basically what you guys are doing in the lab. So, right? Yeah. But that case is more complicated because that's a weak acid. We're going to talk about that. But here we observe that using a simple mathematical description by just doing the same thing as we used to do. Quickly check. If you do calcium, the concentration of acid equal to the concentration of total, which is basically at 1 millimolar, then this term would be 0. Then Kw goes this way, and then you get pH of 7, right? Or at pH of 7, if you go this way, the X value is basically equal to the total concentration of sodium, just going from the opposite direction. So this was the simplest case when you have only a strong base, or it could be opposite also, strong acid in your sample. So the second scenario is when you have a weak acid or base in your system. So this might be a little bit more involved as you can guess, because a strong acid, strong base, first it fully dissociates, and then that means it's directly related to the concentration, the initial concentration. Weak acid, it doesn't fully dissociate. It's basically depending on the alpha term. That species concentration divided by the total is basically alpha. When alpha is 1, then it seems it's fully dissociated, but it's not the case all the time. So it could be a little bit more involved. So here we want to look at the titration of a weak acid, which is acetic acid, and HAC, let's call it. pKa is 4.7, and we're going to use sodium hydroxide as a titrant. This is very... So the first thing is, as always, we look at what kind of reactions we have and how these reactions are introducing species into the system. So again, acetic acid is in the sample. The titrant is sodium hydroxide. So what's the reaction? As always, we have H plus OH minus, like the previous case as well. And this is Kw. What is the second reaction? We have a weak acid, so it might deprotonate. So what is it? Exactly. So AC minus plus H plus. And this is because it's written in the standard notation, so then we can basically, the K value would be Ka for this reaction. So based on these two reactions, what are the species? Yep. Mm-hmm. Exactly. And we're bringing sodium also to the system, sodium hydroxide. The reason we don't have any further reaction because sodium is not reacting with any of the species here. Partially, it might react with AC minus, but we're ignoring that. But in reality, it might. So some of it would react with AC minus. So now we can do a little bit of mass balance. Eventually, what we want to do is simplifying charge balance. So the best approach is going through mass balance. And we want to use alpha. Alpha 0 is HAC over the most protonated version divided by the total AC, which is a known value. Alpha 1 is also AC minus total AC. And then, this has to be, this is equal to H plus H plus plus Ka, and this would be equal to Ka H plus plus Ka. Also, another one from mass balance would be the total sodium is equal to, this would be sodium, is equal to total sodium, which is equal to the C, this time Cb, how much acid we're adding. This is something that we have control on. And if we have like a typical charge balance for this reaction, then it would be all the positively species. Sodium plus equal to hydroxide plus AC minus, and all of them they're like monovalent. So, and now what we do basically revise the charge balance by combining all the mass balance we had. So basically what we're gonna do is put this one, and this one into the charge balance. I mean, not this one, but this one, because AC is here. So it would be this one times this, and then this directly goes here. And then for this one, it would be Kw over H plus as before. So then the charge balance would be revised to H plus to the power of 3 plus Ka plus Cb, H plus 2 plus Cbka minus Ka total AC minus Kw H plus, longer than expected, minus Kw times Ka. So that's the equation for the line of the titration. So what we do as before, change Cb, then this would be a polynomial equation. We solve for H plus, therefore the pH. So then this would be X value, this would be the Y value. So again, if we have this a known value, then this would be constant, this is a constant, and this is a constant. And this would be a typical polynomial or cubic equation in this case. And if we actually do that, this would be the curve. So this one you can construct that kind of titration curve in Excel. Or Excel might not be the best case, but like let's say MATLAB or whatever programming language you use. So it's sort of a loop every time you're solving for a cubic equation by changing Cb from, in this case, from 0, let's say, to all the way to 0.02. So the good thing is about this equation is, to some extent, this is an advanced version of the algebraic solution. So this is, if you have Cb equal to 0, then it gives you the pH of the system. What would be the pH of 10 to the minus 2 molar acetic acid? So if you put Cb equal to 0, then it would be the initial pH. And here it's equal to that 0 of added base. So this would be basically our initial pH. And it seems this is the sharp change. And here we got this delay. So from the initial point, it seems it has resistance, or as we talked about in the next lecture, sort of a buffer zone. And we're adding a lot of base, but it doesn't change. But immediately here, we have a sharp increase. So we depleted all the weak acid, or we deprotonated because we're adding base. We deprotonated all the weak acid. If we were adding acid, we would protonate all the acid, so the rest would go to the pH change. So what does it mean, like minus sign for Cb? We took out some sodium hydroxide from the system. What could this be? You also do double titration? Okay. So this is sort of a double titration. It seems like you first did acid titration, then base titration. So when it's basically Cb, which is the concentration of base, so the positive value would be base added, negative value, this is acid added. So you can do it experimentally. You can basically have the sample, add acid, and then the pH goes down. And then this is, because of that, this is equivalent of like how much acid you added. And then you connect that tail to the base tail. So you get the whole spectrum of the pH changes. So here, from here to here, you're mostly protonating. So you're mostly AC minus is protonated. So that's how you're consuming proton or resisting against a big change. And this way is basically opposite. So HAC is producing H plus plus AC minus, or this is basically consuming hydroxide. So when we look at the delay, it seems it's between 4 and 5. Is it random, or this is related to something else? If I was doing like titration, Exactly. So pKa was 4.7. So this is around pKa, which is 4.7. So this is the second important information we can get from titration. First thing, we could calculate how much of that acid or base we have in the sample by knowing how much delay in terms of the x-axis. So here in this case, for example, getting from here to here, it requires 10 to the minus 2 molar of base to be added, which is exactly equal to how much acid we had. So that's one information. The second information now in terms of the y-axis, the delay is around pKa. So you can guess, if I'm giving you an unknown sample, you can quickly do titration, tell me how much of the total acidity it has. Also tell me potentially what kind of acid you might have in the system, because the delay is around 4.7 in this case, and then you look up in table, and then you say, oh, we might have this one. So we're going to talk about that later. But this was the second scenario, adding strong base or acid to a weak acid and base. So the third one is the combination of the first two. You have sodium hydroxide in your beaker. You also have some weak acid. And now you want to see what's the profile, right? So we don't want to do like quantitative on this one, but we could. But it's easier to go qualitative. So in this case, specifically, we have 10 to minus 3, 1 millimolar of sodium hydroxide, plus one of these weak acids, one of them. So it's the salt of the weak acid in this two case, and this is basically ammonia. and the same concentration. So we want to see what happens when we add a strong acid. So when we add H plus or Cb, what happens? First, we know it won't change the pH immediately because in the first case, it was consumed by hydroxide. In the second case, it was consumed by the weak acid. We were protonating or deprotonating weak acid. So proton was involved there. It wasn't involved in the pH change. So what happens here? Exactly. So first it neutralizes OH minus from the strong base. So basically you had sodium hydroxide, or so you had hydroxide plus H plus. So this could add a delay, right? You're adding, but it's consumed. And this sodium hydroxide is coming from, this hydroxide is coming from sodium hydroxide. So then let's say we deplete it or we neutralize all the hydroxide. Then what happens? This is not a sequence. This is just, it might happen at the same time. So what's the other source of consumption of that proton? Exactly. So it protonates the weak base. Or weak acid or base, depending on how we're looking at it. So for example, in the case of OCl minus, then it consumes proton that's introduced by that Ca factor. And then it's basically protonating. And this is coming from so it seems that that is adding also a delay. So if we have that as a function of Ca, pH of the system, which includes 2, then we're expecting something like this. The first delay, then the second delay, then the sharp decrease. So it would be something like this. So this would be first delay, this is the and then this is basically a sharp drop. So again, titration was useful to elaborate on these two, or the species in the system. Because similar to the previous two cases, we know the resistance is related to the concentration. So this part is related to the concentration of sodium hydroxide. This part on the y-axis is related to the concentration of the weak acid or weak base we had. So, and this is basically all of them together, combined together. And when we look at it, this part is like delay related to sodium hydroxide. And then roughly when we look at it, it's around 1 millimolar equal to the concentration. As you see, the second delay before we get to the sharp decrease is roughly around 2 millimolar. So this is basically so on the x-axis is the concentration. So you were guessing if we had more of the weak acid, then it would be something like this, and then like this one. On the y-axis is related to pKa. So if we go higher, so this one is, the black curve is basically sodium hydroxide by itself. So only one delay related to sodium hydroxide, then a sharp drop, and then the rest would be as we were expecting. Then the red one is the salt for acetate. And when we look at it, roughly this is basically the delay zone on the y-axis, and roughly in the middle is where we have the delay. And when you look at the pKa, basically this was 4.7. Again, it's near the pKa. For the green OCl, the value for pKa is 7.5. And when you look at it, so this is the delay for green, and roughly is around pKa. So that's center point. Only looking at ammonia, this is the delay. This is the delay zone, roughly around 9.2. So we analyze both on the x-axis, which is the concentration of each, and more importantly on the y-axis. So by quickly looking at this, seeing where this delay is happening on the y-axis, you can tell basically what kind of acid you're using or what kind of pKa. And this was a mixed system, not just an individual. So now we can basically twist the question and say we have this solution, which the initial pH is 11. The initial pH is obviously 11 because it's mostly dictated by the sodium hydroxide. And if you do the calculation, you get to that 11 also. So pH is 11, the initial point. Now, how much acid you need to get to pH 6? Or how much resistance you get on the way from pH 11 to pH 6? So to get to pH 6, so you're expecting more of the resistance you have. Definitely you need more acid to be added. But now we want to see the difference between different weak acid. So what would be the case for sodium hydroxide only? How much? Exactly. So when we look at pH 6, and when we do, where it cuts this black curve, then it would be 1 millimolar. Or how about for sodium hydroxide plus NaOCl, which would be the blue curve. Let's see. So we have to cut this blue curve. 2. Okay, so let's do green. Let's do 2. But then it would be 2 millimolar. So I think you get the point. Like, we need more acid to neutralize that. So now let's go back to the beginning of the lecture. Right? I told you like this could have two kind of interpretation. One is we basically add acid and base and get important information from the system. But then the second one is sometimes we really need to neutralize it. For example, you have a wastewater coming out from a plant that has a pH of 11. Then you need to know how much you need to add of that strong acid to be able to get to that threshold of safety, which let's say is 6. Depending on what you have in the system, you might need to add different concentrations. So this is also a second kind of information we can get from titration. So again, very useful. Just keep in mind, this is related to concentration. This is related to pKa. Okay, so again, generalizing that information. The pH near pKa, it's basically you have that delay zone, or pH changes very gradually. So that's related to the pKa. So the titration curve will have flat portions near the pKa of each of them. So what we also talked about. And also we combine different kind of weak acid and also strong acid or base. This could be also done by combining all the three together. So you get that sort of delay, the sequence kind of delay. In the previous example, the pKa were far away from each other. So 4.7, 7.5, and 9.2, for example. Far enough to see if you have a sample that is a mixture of all of them, you still be able to look at that and then figure out what potentially you have in the system. But sometimes when the pKa's are very close to each other, you might not be able to see it. So it might overlap so much. So in this case, we combine all of them together. So 10 to the minus 3 sodium hydroxide, then 0.4 millimolar of sodium acetate, and then the other concentrations of the other. What we did was first doing a very simple titration for sodium hydroxide to be able to differentiate between the second scenario, which is basically a mixture. So first we get relatively flat near pKa. And also, as we mentioned, the width for the flat portion is proportional to the concentration for each specific acid or base that we have in the system. So now if we look at this system, it might not be very obvious, but to some extent we can tell. So this part for the red curve is just because of the sodium hydroxide. So it's similar also to the other curve, which is only sodium hydroxide. Now we get to this part that has like from here to here roughly, or a little bit further. And then from here, no, it's really hard to. From here to here, so that's one flat, second flat, and then you have a sharp decrease here, and then you get the bottom one, roughly here. So this is related to I'm just writing the actual, oh wait, not for this one. This has the highest pKa, so this is for ammonia. So now roughly 9.2. So roughly 7.5 is this one. This is for HOCl, and 4.7, so we need to work a little bit on this one. For the acetate. So the width is the concentration, and then near what kind of pKa is basically telling us what kind of acid we have. So the good news is we have titrators, automated titration setup in the lab, and that would be one of the demonstrations we will have at the end of the course. So we go to the lab, and then Kara would help us to run some titration. Basically what it does is constructing that curve and then data interpretation. What kind of acid you have, potentially, and you have to be lucky not to overlap or not to have like acid with nearby pKa. And then what's the concentration of each? So the last scenario is, so far we talked about strong acid, weak acid, strong and weak together. And now we want to talk about a multi-product acid. The previous one was always about a monoproduct. This case is basically a polyproduct, or in this case, biproduct. So here we combine sodium hydroxide, which is this black curve, with sodium carbonate. And once we have sodium carbonate in the system, we know it fully dissociates to sodium plus bicarbonate. And then we know bicarbonate can combine with carbonate to produce bicarbonate. And then bicarbonate can further combine with proton to form carbonic acid. And we know this one is pKa 2 and this is pKa 1. And if we have the titration for this system, normally it looks like this one. So the first delay is because of sodium hydroxide, and the next delay, roughly up to here, is related to pKa2, or sorry, this could be and this is basically carbonate is consuming a proton, and then you have a sharp decrease following by the second one, which is pKa1. Here bicarbonate is consuming the proton, then the rest is basically following by. So it seems you have, so scenario 4 could be similar to scenario 3. It seems you have two different weak acids, but it's basically coming from the same species. And when you look at it, look at the concentration. This is 1 millimolar for sodium hydroxide, which makes sense, 1 millimolar. But now you have only 1 millimolar of sodium carbonate. But then when you look at it, you need overall roughly 3 millimolar. One of them is because of the sodium hydroxide, but then the fraction you need to neutralize sodium carbonate is 2, twice of the concentration. because this can be looked at as two different weak acids. So again, in terms of the concentration term and also in terms of the pKa values. So the last part, it's titration of a sample with unknown concentration and unknown species. So we talked about this briefly. The idea is basically very similar. In the previous case, we had a good idea of what is in the system, what kind of acid base, and we observed that that delay is related to the pKa. But now we want to use that, like getting that pKa, and then trying to see potentially what could be there. So we take this sample, unknown solution, and we bring it to the lab, do titration, a typical titration, but here it's double titration. It's been using acid, using base and acid. And then we look at the profile of how that profile is changing. And then we compare it to the blank sample. So this is a blank sample of only pure water, because eventually there's water there. So we want to subtract the impact of water and then specifically look at what is there, because this is a combination of water and whatever we have there. So if we have this control experiment, then we can basically subtract it. So now we know initially the pH was around 6.8. So this is the first thing we see. No acid added, no base added. So we know this way is basically acid added. This way basically base added. And the question would be how we can use this graph to interpret what we have potentially. And then what's the concentration? So right now we did titration to go from pH, or to swing between pH of 3 and 11, as you see on the graph. So the pH between 3 to 11. So for this swing of pH, how much for water, how much equivalent acid we need? Going from pH 3 to 11. So can we say this is the profile? So we need this much, or 2 milli equivalent per liter. Again, this is equivalent, acid plus base. So we need 2 milli equivalent per liter to change the pH from 3 to 11 for water. How about the sample? So the red one, to get from pH 3 to 11, how much equivalent we need? 5. So good. So we know sample also contains water. So how much total acidity we have? Besides water? 3. So 2 out of this 5 was because of water. So now we have 3 milli equivalent per liter. So we did a very simple test. We figured out what's the total acidity of this sample. 3 millimolar of acidity we have. So if you want to neutralize it later, you have this titration curve to figure it out. So it seems the graph is flat around in this range. So the middle point is roughly here, right? So pH curve, flattest, around 6.5. So therefore, if we have one acid, then the pKa is roughly 6.5. But as we talked about, this could be way more complicated than that. But here it seems it's relatively simple. So getting this kind of curve for like a dirty sample, it's a pure luck because the curve is not normally as neat as this one. But here it seems this is a gradual decrease in pH. And then we can say roughly this is somewhere between here, between 7 and 6. So roughly 6.5. With some intuition and using standard tables, we could hypothetically talk about potential options. For example, if this wastewater is coming from a copper plating industry, we look at the table and then we say, oh, we have roughly 5 options that could have a pKa of 6.5 roughly. But then only maybe 2 or 3 of them are possible based on what is coming out from the copper plating industry. So that kind of combination of intuition plus the information from the titration could guide us on what we have here. But what we know for sure, if we want to neutralize this from 6.8 to whatever value, let's say 7, we know how much we need to add. So for pure water from 6.8 to 7, it's almost nothing, very, very minor. But here from 6.7 to 7, we need this much, almost 0.5 millimolar to be added because of the resistance. And that resistance, as I mentioned, is basically a buffer, which is for next lecture. In the next lecture, we're going to talk about buffer, in different scenarios. So again, that was also some sort of useful information. To do a quick practice, just look at this graph we have for pure water. In this case, we only added, we also added base. So we added both base and acid. And then we want to see hypothetically what this could be and what's the concentration based on what we had in the previous pages in terms of the acid. Like it's one of those acids probably. So what's the concentration here? The total concentration, if we have that one acid. Why is that? So you're going from 0 to here, right? But still you're in the delay zone. So you have to keep going to this point. Then you have a sharp increase, right? So until here, still resisting. So this would be the value. Make sense? So the total acidity is 0.01 equivalent per liter, or which is roughly 10 to the minus 2 molar. What you mentioned is actually correct for the pKa. Yeah, that tracing that. It's technically speaking, it's called equivalent point, the first equivalent point, and those sort of. So this is the first equivalent point. This is f of 0.5, and then at f 0.5 you get to pKa. We had that 2 years ago, but now I eliminated it because it doesn't add much information. But that's basically that 0.5 of equivalent. So roughly, what's the range of pKa? So from here to here, as you mentioned, is 0.5 of the equivalent point. So this is pKa. So pKa of roughly 4.5. What could be this one? Based on what we had in this lecture, one option could be acetic acid. So HAC. So probably this is a titration of 10 to the minus 2 molar of HAC. To make sure you can basically make 10 to the minus 2 HAC in the lab, do the titration for that, and then see how much overlap they have. That's one way to confirm it. Because this might be a very complex matrix of species that eventually get to the same similar curve. To just highlight the impact of concentration, here we have pure water. We're adding base. As you see, the pH increases. And we have acetic acid, two different concentrations. And concentration only impact how much acid we need to add, right? So the buffer zone in terms of the x-axis is changing. So this is 0.01 almost, but here in this case is 0.02, which is proportional to the concentration of what we have. However, because these two are the exact same acid, the pKa should be the same. So the middle point for this zone and this zone should be both the same. Roughly pKa of so the delay for both would be the same zone, but it's basically more gradual for this one because you have more to neutralize compared to this one. Twice more compared to that one. So when you see sometimes like something like this in the exam, by quickly look at pKa, the range of the buffer, you can tell whether this is one kind of acid or two different kinds. And then by looking at the x-axis, you can basically talk about the concentration. So this could be a typical question in the exam. Okay, so we talked about qualitative description. It's all about the consumption of that acid and base that you're adding by something that is in the system. Could be hydroxide, could be acid, it's H+, or it could be a conjugate base or acid that is eventually consuming. And it's not letting or delaying the change, sharp increase or decrease in pH. We also did some quantitative description using just basically a charge balance equation. But you could also do it in Visual Mintek, so the software that we talked about in the previous lecture. I briefly mentioned that there. We have this sweep function. So when you do the sweep function, you can basically sweep anything you want. Here you can change the CB or CA, sweep that one, and then look at the pH as the y-axis. We used that to construct PCPH in the previous lecture. We sweep the concentration of proton, which is the pH x-axis, and then we looked at PC for different concentration of different species. So this can be done easily using Mintek as well. Just basically this shows how to work with that sweep function. So sweeping something that is, in this case, we're calculating the concentration of proton as the y-axis. The concentration of proton. And this is what we're adding, which is, in this case, adding acid. And eventually you can get how much you added as the x-axis, and then log of H+, which is pH. So this is the y-axis pH, and the x-axis, which is how much added. And then you get something like this one. So instead of doing that control experiment in the lab to make sure that's acetic acid, and then comparing it with what you had, you can also simulate it using Visual Mintek. That's why this is a very useful software, and of course it's free. So by just using that sweep function. Okay, so to wrap up, we talked about titration. Titration was a very useful term, a useful experiment. First, because it's very easy to conduct. You just need a pH probe. You need to add a known acid, strong acid or strong base, to an unknown. And then you were able to interpret the data that is basically related to the trace of pH as a function of how much H plus or OH minus added for that kind of graph to be able to look at the total concentration, also looking at pKa of that species you have. So this was two important information that we were able to get from a very simple experiment, which was the titration. As mentioned, this could be more involved, but always bringing some intuition from the system can also help us to get the most accurate answer.